I want to talk about something that we've seen a couple times already with random variables, but we didn't give it a name yet. It's called exchangeability. Let's let x1 through xn be n discrete random variables. We're going to call them exchangeable. If we have the probability that x1 equals some number a1, x2 equals some number a2, etc., equals the probability that x1 equals b1, x2 equals b2, etc. Whenever b1 through bn is a rearrangement of a1 through an. Equivalently, if we let little p be the probability mass function, the joint probability mass function for these n random variables, I'm saying that p a1 through an equals p b1 through bn whenever b1 through bn is a rearrangement of a1 through an. So seeing it's really the multi-set of numbers that matters and not the order of those numbers. So for example, let's say an urn contains 4 blue and 6 white marbles. Let's choose 3 without replacement. And let's let x1, x2, x3 be the colors chosen. So I claim that x1, x2, and x3 are exchangeable random variables. So that is, if we look at the colors, the order that the colors the order that the colors come in doesn't matter. It's just the collection of colors. Now the probability that we get blue, blue, blue is uninteresting here because there aren't any other orderings of blue, 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 or white, white, white. So these don't matter. But let's consider the probability of getting 2 blues and a white in that order, or blue, white, blue, or white, blue, blue. I want to show that these all have the same probability. So to get a blue first, we've got 4 blue out of 10. So that's 4 tenths. To get a blue second, there's 3 blue left and 9 marbles total. To get a white, there's 6 marbles total that are white out of the 8 marbles that are left. And then if we get blue first, 4/10 again, white second, then there's 6 white out of 9 marbles left, and if we get blue third, then we already chose 1 blue, so there's 3 blue left out of 8 marbles left. And if we choose white first, there's 6 white out of the 10, blue second, there's 4 blue out of the 9 left, and blue third, there's 3 blue left after we take 1 out of 8 marbles. If we look at these fractions, we've got, let's see, 4 times 6 is 24. 24 over 8 is 3. But 3 times 3 over 9 is 1. So each one of these is just 1/10. Again, we've got 3, 4, and 6 in the numerator, and then 10, 9, 8 in the denominator. So they're all the same. And we could do this the same with 2 whites and a blue. Two whites and a blue, the probability of white, blue, white, and the probability of blue, white, white. These all turn out to be 1/6. So, well, that's all we needed to check because we looked at all 8 possibilities of what could happen when we choose 3 marbles. Now, just to look at a slightly different point of view, let's look at the blue, blue, white, the 2 blues and 1 white possibilities. So the number of ways, instead of multiplying 3 different probabilities, we could look at the number of ways to get blue, blue, and white, which is 4 ways to get the first blue, 3 ways to get the second blue, 6 ways to get the white, blue, white, blue, 4 ways to get the blue, 6 ways to get the white, 3 ways to get the second blue, and white, blue, blue. So there's 6 ways to get the white, 4 ways to get the first blue, 3 ways to get the second blue. If we look at it this way, maybe it's clearer that we're multiplying the same numbers, just in different orders. So the probabilities are all 4 times 3 times 6 over 10 times 9 times 8, because the number of ways to choose the first marble, second marble, and third marble are always 10 times 9 times 8. So one way to recognize exchangeability of, let's say, n random variables is to see that the number of ways to get outcomes A1 through AN equals the number of ways to get the outcomes B1 through Bn whenever B1 through Bn is a rearrangement of A1 through AN. So let's do this problem in a little greater generality. And see that it's exchangeable by using this argument. we had just we were choosing a small number of marbles, so it was easy to do the computations in the last one. But in general, we couldn't use those computations because we wouldn't be able to do all of them if we're using general letters like N and M. So let's suppose that an urn contains capital N marbles, and little m of them are blue, and I guess capital N minus little m are white. Let's choose little n without replacement. And let's let the random variable xi be the ith one, the ith color chosen. Then I claim that x1 through xn are exchangeable. Alright, so we'll try and prove it using this idea. We'll just count the number of ways to get different outcomes. So the values of x1 through xn will be a rearrangement, something like blue, white, blue, blue, white, blue, white, white, etc. of some number of blues and some number of whites. Let's say we have I blues, and we picked little n total, so there'll be little n minus I whites. So I is going to be a number that's less than the number of blue we have. I is less than m. So we get some rearrangement to this, but no matter which rearrangement, of the colors, the number of ways to get it is so there are m blue marbles. So there's going to be m choices for the first blue marble. Whether it's in position 1 or position 2 or position 3, wherever it is. And then there's going to be m minus 1 choices for the second blue. And then m minus 2 choices for the third blue, etc. And if we have a total of I blues, then m minus I plus 1 is the ith blue, times, so let me just write down here, n marbles, n blue, capital N minus m white. So times, we can choose the first white in n minus m ways, and then the second white in n minus m minus 1 ways, And if we're choosing little n minus I, then we can choose that n minus ith white marble in capital N minus m minus n minus I plus 1 ways. So this is the first white marble, wherever it is. It could be position 1, position 2, wherever the first white one is. And this is the second white, etc. And this is the n minus ith white. So we're going to get the same number no matter what order those blues and whites come in. And then if we're going to write probabilities, so we could say this product is the numerator of the probability, and the denominator is, we're choosing n, so there will be capital N for the first marble, capital N minus 1 for the second marble, and capital N minus little n plus 1 for the nth marble. So no matter what the order is, this probability turns out to be the same thing. Right, now a nice property of exchangeability is that if we want to compute the probability of something happening to the ith random variable, it's the same as the probability of that same thing happening to the first random variable. So if x1 through xn are exchangeable, then they're identically distributed. In the sense that the probability that x1 equals some value c equals the probability that xi equals some value c for I equals 1 to n and whatever value. So to see this, well, let's compute both of these probabilities and show that they turn out to be the same thing. So these are both marginal probabilities. The probability that x1 equals c is the sum of, let me give myself more room. The sum of the probabilities that x1, x2, x3, etc. up to xn equals, let's see, x1 is going to be c definitely. And then x2, let's say, is going to be b, and x3 through xn are going to be Actually, I'm not going to use a b here. So we have n minus 1 other values. I'm going to call them a1 through a n minus 1. And let's sum over all possible collections of a1 through a n minus 1. We're going to leave the c fixed. So by definition, we have this expression for the probability x1 equals c. And let's look at a2, sorry, x2. So instead of general I, we'll use the second one. The probability x2 equals c is the sum of x1, x2, x3, etc. up to xn equaling a1, c, and a2 up to n minus 1, summed over all possible values a1 through a n minus 1. I meant to write the a2 up here also. Alright, so we've got expressions for probability that x1 equals c and the probability that x2 equals c. But by the exchangeability of x1 through xn, every probability in this sum should be equal to every probability in this sum, because changing the orders of the values that we get doesn't make a difference. So each term in the first sum equals the corresponding term in the second sum. So that means that the probability that x1 equals c equals the probability that x2 equals c for all c.